statistics students. So let's finish up chapter 8. You know about hypothesis testing. So now in 8.4, the last of chapter 8. So after this, you'll be able to do the chapter 7, chapter 8 quiz. In 8.4, we're going to talk about dealing with two population proportions. Okay? So that's our big goal in 8.4. And so it's basically just going to take that hypothesis testing that we talked about, and we're going to modify it just a little bit, dealing with two populations. Because sometimes you have two populations that you want to compare. Okay? So first things first, let's talk about some of the differences that happen in here. And then I will show you on the graphing calculator and StatCrunch how to do this. I'm not going to do this by hand, although some of these pieces we will do by hand. But most of the time, we're just going to let StatCrunch and the calculator do the heavy lifting for us, okay? So let's talk about some of the differences, what's new here. So again, in here we are changing up the hypothesis testing just a smidge, and we are dealing with two populations, okay? Not one, but two. So in step 1, when we are stating the hypotheses, things are going to look a little different. So for your null hypothesis, you're going to say population 1 equals population 2, okay? Population 1 equals population 2. And you're not going to have the numbers for these. This is how it looks. P1 equals P2. Although there are some technologies out there where they'll actually have P1 and P2 on the same side, and it will look like this. P1 minus P2 equals 0. Okay? P1 minus P2 equals 0. All right. So then the alternative hypothesis is all about whether they're not equal or whether P1 is less than P2 or P1 is greater than P2. Okay? So let me give you kind of an example and put this more in perspective for you. Generally, when you look at two population statistics, when you're dealing with those two pieces, most of the time it's because they want to know have things changed in the population. So say that we took a survey back in the book 1961 is stuck in my head because that's an example that they use in the book. And they are talking about, well, I can't remember what they're talking about, but let's just say it's about whether they believe the boogeyman is real. We'll just throw that out there, just something stupid. Whether they believe the boogeyman is real. Okay. And then they took and did a sample with today's population about whether the boogeyman is real. Something along those lines. So we're comparing two different sample populations there. Okay. So we want to know the null hypothesis is basically saying there's been no change. What happened in 1961 is still the beliefs in 2019. Okay? Or the alternative hypothesis, using that example that we talked about, maybe there has been a change. They're no longer the same. So that's when we do the not equals. So when we say that we believe it's changed, you want to talk about a not equals. Okay? Or maybe we believe that the people in 1961, that there were fewer people than versus today. So we believe that there has been an increase. Okay? So this right here says that there has been an increase in the perceptions. So there's been a change. We believe that the perception that there is more. So that's what this is saying. Okay? And then down here, we believe that there is fewer today. Okay? So 1961, more people believed in the boogeyman than what happened in 2019. So those are the alternative hypotheses we go about. We just believe that it's changed. We don't know whether it's greater or whether it's smaller. We just believe it's not the same anymore. Okay? Or we believe that today's population is, excuse me, today's population is greater than the old one. And I know I said greater, but that's because I'm looking at it backwards here. Okay? Or we believe that the past population is greater than the current population. Okay? Again, just like before, though, they might write these in terms of P1 and P2 on the same side. So these will look like P1 minus P2 not equal to 0. Or P1 minus P2 less than 0. Or P1 minus P2 greater than 0. So they could be written like that. All right. Just to kind of talk about some things right here. It does not matter which population you call P1 or P2, but you do need to keep that in mind when you're thinking about the alternative hypothesis. So I said P1 was 1961 and P2 was 2019. As long as I remember that, I'm A-okay. So you know what the book does and what they like to do. They usually let the newer population be P1. Okay? So usually the more recent population is P1 and the older population is P2. Okay? So that's what I said right here. My general suggestion is that most recent set of data are P1. Okay? Also, again, like I said, as long as you know which one is which, that's the important part. So it doesn't matter which is P1 and which is P2. Also, so you know, the finally, in this one, the null hypothesis does not tell us about the value of the population. Okay. So the null hypothesis does not tell us what P equals. So with that being said, because of that, we are going to estimate the null hypothesis value by pooling the two samples together. You will see that come up in the next slide when we talk about, excuse me, the preparation part. Okay, so because the null hypothesis is not telling us about the value of the population, because all we're saying is population, what happens now or then is the same as what happens now or then. Again, depending on how you say these. Okay, so we're saying that they're still the same, but there's no numbers here. There are no numbers up here. We will not be plugging into P1 or P2. Okay, so you'll see how that works here in just a couple minutes. All right. So because we do not know the value of the population, our null hypothesis doesn't tell us that. We're going to be pooling the two samples together and using those to create an estimate. And you'll see that here in just a second. Okay. Again, up here, you are not actually plugging in to these. You will leave them the way they are. So the null hypothesis looks like this 100%. The alternative hypothesis looks like one of these three. Okay? Again, over here, this is what some of our, excuse me, some of our technologies, this is the way that they write it when it is a two-sample population. Okay? So there's step one. There's the changes to the hypothesis. Step two, changes that happen here. Know that you're going to be performing what we call a two-proportion Z statistic. Okay? So in the calculator, show you where this is at. Again, it's under stat, over in tests, and this is where we did, this is the original hypothesis testing right here. Here is the two-proportion Z test. Okay? So 5 is the original, 6 is the two-proportion. All right? Just checking something out. So 6 is the 2 proportion z-test statistic that we want to run. Okay. In StatCrunch, show you that one real quick. So in StatCrunch, you go to stat, down to proportion stats, and this time you're going to do 2 sample with summary. So proportion, 2 sample with summary. Okay? All right. So let's cancel that out. So now you know where they're located. In here, when we check the CLT, things have changed a little bit for us. You still also state your significance level in here. That hasn't changed. But the changes to CLT, there's a little bit, okay? Because we have 2 proportion samples now. We got a little bit more work to deal with, okay? So the first thing is large samples. Okay, we need to know our sample size is large enough. Remember, that's the successes and the failures. And because we have 2 samples, we got to check both of them for successes and failures. Okay, this is going to be that estimated null hypothesis that we're talking about. Okay. That's what this is going to be. This is going to be that estimated null hypothesis value that I was talking about right over here, where I said we're going to pool the 2 samples together. So P hat over here is that estimated null hypothesis proportion value. Okay? So you got to check it for both samples. So this right here is the total of sample 1 times our estimated value. We want to make sure it's over 10. This is the total from sample 2 times our estimated value. We want to make sure that that's greater than 10. And then over here, we check the failures for both of them. How do we find P hat? Let me show you. So what you're going to do is you're going to take the successes in sample 1 plus the successes in sample 2 and divide that by the 2 totals added together. See what they mean by pooling the resources. They take all the successes in sample 1 plus all the successes in sample 2 and then divide that by the 2 totals added together. So that's where our estimated value is coming from. Okay? So we got that. So that's the first change. We got to make sure that they are large enough samples. All right? Second from there, again, you got to make sure that your samples are random. Okay? Both samples must be random. You got to make sure that both samples are independent of each other. Okay? So those that believed, kind of going back to my boogeyman case, those that believed the boogeyman in 1961 should not affect those that believe in the boogeyman in 2019. Okay? And then you also have to make sure that the observations are independent within the samples. So everybody we talked to in 1961, all their answers were independent of each other. And the same thing in 2019. I don't know why I'm saying 2000. I should be saying 2020. 2020, those that believe in the boogeyman, all their responses should be independent of each other. Okay? So 2 types of independence here. We got to make sure that the samples are independent of each other. So those in 1961 don't affect those in 2020. Okay? And then you also got to make sure that they're independent within the samples. Everybody that answered in 1961, their choices cannot affect each other. And everybody that answered in 2020, their choices cannot affect each other. Okay? And that's it. Those are the new kind of pieces. We don't worry about whether the population is large enough. Okay? We don't have to worry about that. We just got to worry about this information. Okay? And as long as all 4 of those are met, it is normally distributed. Okay? We're back to a normal distribution. So again, just some minor changes. Oops, sorry, I had something on my screen and I was, come on now. That I was trying to get off. All right, so there we go. There's just some small things to step 2. That's it. So a new test statistic that we're running and a couple of changes to CLT. And then finally in step 3, I want to show you the math that is going on, the math that your calculator is running. And again, you can run this by hand, but I don't want to. Okay, I've got technology to help me out. And I didn't mean for that to pop up there. So let's quit that. Sorry about that. So let's talk about the math that's happening. So the first thing is you want to figure out your Z statistic. Okay, so this is the math that your technology is running. In order to find your Z statistic, you're going to take your estimator minus the null value. Okay, so the null value, if we kind of go back and talk about this, because they are not, because the null value says that they're equal, when you subtract those two, you get 0. So that's where this 0 you see in here is coming from. Because P1 minus P2 is, 0. Then over here, the estimator, well, this P hat is when you actually take the successes divided by the totals for P1, your population 1. And this P hat is when you take the successes divided by the total for your second sample. So this is actually figuring out the probability of success for your first sample minus the probability of success for your second sample. So that's the estimator. That's right there. These two, P1 hat minus P2 hat, is the estimator. The null value is always going to be 0 because we are assuming that they are not changed from the beginning. They are the same. And then down here, this is your standard error. Okay? So there's a formula for it, and the standard area formula got just a little bit bigger because we are going to be pooling the two pieces together. Okay? So we are pooling the two pieces together. And I feel like I'm missing a symbol in there. Let me double check. And I am. This should have a hat on it. So my P's in here should have a hat. Not my fault. Oh, that should be a P hat. And that's that value we estimated from the beginning that we were using to check our successes and failures. This is that same guy. Okay? Ooh, almost messed that up. Let's group all that together. And then, so you're going to take your, excuse me, P hat, estimated value of the null hypothesis, times 1 minus P hat. And then you're going to multiply that by 1 over the total for sample 1 plus 1 over the total for sample 2. Okay, so 3 values that get multiplied together. All right. And I believe that's it. Yeah. So this is the new math that our technology is running. See, again, this is why I don't really want to run it by hand. All right. But we can if we need to. Okay. You've got all the formulas for these. And again, this P1 and this P2 hats, these are just the probability that happened in your sample 1, your successes divided by the total. And this is the successes divided by the total that happened for sample 2. That's what those are again. Okay. All right. So let's answer some questions. So right here, I've got a thinking question. I actually got 2 questions right here, just in general about what we have seen. Okay. Oops. Again, I got stuff on my screen that I'm trying to get rid of. Perfect. Got it. All right. So when comparing 2 sample proportions with a 2-sided alternative hypothesis, so in other words, not equals, okay, all the other factors being equal, will you get a smaller p-value if the sample proportions are closer together or if they are far apart? Explain. So once you figure out remember, the p-value doesn't change. We find it the same way because it's normally distributed. So they're asking, and remember what we talked about before, the larger the z value, the smaller the p-value. So we're going back to that concept. So they want to know, based off of the proportions, okay? Based off your P1 proportion, P2 proportion, will you get a large z value if they're closer together or if they're further apart? The proportions. So think about that for a moment. Is it better to have these closer together or further apart? And go. Okay. So in this one, the answer to this is you want them to be further apart. Reason being, because the further these proportions are apart from each other, the further those probabilities are away from each other, the larger the numerator is going to be. The larger this numerator is going to be. Okay? And the larger the numerator, the larger the z-score, because hopefully this is going to be a small number that will divide it. Okay? The larger the numerator, and hopefully this is a small number, the larger that z-score. Okay? All right. So with that being said, answer this question. When comparing two sample proportion with a two-sided alternative hypothesis, all other factors being equal, will you get a smaller p-value with a large sample size or a small sample size? So now you're talking about that sample size, and sample size is played in with this. Do we want a large sample size or a small sample size? What do you think? Okay. So, oops. What we want in this one is we want a large sample size. Here's why. To create a large sample size, notice that my sample sizes affect this piece right here. The larger the sample size, the smaller this number is going to be. The larger the sample size, the smaller this number is going to be. And the smaller this number is, the more it's going to raise the z-score. The smaller this number is, the more it will raise the z-score. Okay? So there you go. Okay? So if we want p-values to be small, we want large numerators, small denominators. Okay? All right. So here we go. I've got two examples where we're going to go through the full testing. Okay? So in this, let me walk you through one. And then right here, I've got another example. Okay? So let's walk through this one together so you can experience it. So it says Furman reported on a study of patients with reoccurring chronic lymphocytic leukemia. So CLL, and that's what I'm going to call it because, yeah. All right. So the study was randomized, double-blind, and a placebo-controlled. And that's huge. Okay. So after 12 months, 101 of the patients assigned to the combination treatment of IDEL with RIT, because I'm not going to try and pronounce those words, were still alive, and 88 of the 110 patients assigned to placebo with RIT were still alive. So perform a hypothesis test to test whether those who take IDEL have a better chance of surviving than those taking the placebo. Okay. So, first things first, let's figure out who we want to be P1 and P2. So, because there's not any years established with this, I'm going to let my treatment be the P1. So this is going to be the population with the treatment, with IDEL, or IDEL. I'm going to let P2 be the placebo. So I'm writing this down because I think it's important so I can keep referring back to that so it helps me. Now, you already know what H naught is supposed to be. P1 equals P2. And I don't want equals here. I need to make that just colon. All right. Now, ha is either P1 something, P2. So it's either not equals, greater than, or less than. So up here we got it's this sentence right here that's going to tell us about ha. Keyword right here, better. So we want those that are taking the treatment to be more than those taking the placebo. Okay? That's what we want. So when we're down here, now this is why I said you got to know who is who. So P1 is our treatment and P2 is the placebo. So we want this to be bigger than that. So we're going to use the greater than symbol. Now know that if I had P1 be the placebo and P2 be the treatment, I would have used the less than symbol there. Okay? Because it's all about who is who when you're making that symbol. So there's step one for us. We now know the hypotheses. All right, step two, a little bit of preparation. Okay? So step two, we're definitely going to do the 2 proportion Z test statistic. We're definitely going to have alpha equal to 0.05. So let's do some checking of the CLT. Okay? Because in your assignment, they do go through checking the CLT on some of them, not all of them. So again, we're going to check successes versus failures. So before we can do that, we need to figure out what is P hat. Okay? So in order to do this, we're going to need to know the successes for P1, which is the IDEL. So up here, 101 successes out of 110. Okay? So 101. We're going to add that with the successes of the next one out of 110, which will be added with the total of the second population. So P2, we had 88 successes, again, out of 110. Okay? So we go to our calculator, we take 101 plus 88, divide that by 110 plus 110, which is 220. So 100 and show you the fraction. 189 divided by 220 gives us 0.8 0.8590, basically repeating. It's 90909090 forever and ever and ever. Okay? So there's our p hat. Okay, and they're probably going to have you round to 4 decimal places. So if they have you round to 4 decimal places, then we would just call this guy 0.8591. Again, read those fine, the fine print, okay, to let you know. So we'll use this as our p hat. So then now we got to check both. So we're going to take the number that we had in the total number of people for P1, which is 110. It's actually the same for both of them. And we're going to multiply that by 0.8591. And we want to know, is that greater than or equal to 10? And then we'll take 110. I'm going to multiply that by 1 minus 0.8591. And we want to know, is that greater than or equal to 10? Okay? So 110 times 0.8591 is 94.501. And again, we're talking about patients here, people. So you'll probably round that up to 95. Just read the fine print. And again, that's definitely bigger than 10. And then over here, 110 times 1 minus 0.8591. And that gives you 15.499. And again, you'd probably round that up to the next person, so like 15. And again, that's definitely bigger than 10. Okay? So it checks out for the first population. So P1 is all good, but what about P2? Well, thankfully for us, it's all the same information. Okay? So P1 was good, and so is P2. If P2, though, had a different total, we would have to, you would be seeing me write that out, just so you know. Okay? So if P2 had a different total, I'd be writing out the same information again. All right? So just wanted to kind of give you a heads up on that. Okay. So that checks out. So that's part 1 in CLT. So it's good. Part 2 in CLT, are my samples random? And absolutely, it says up here, it is randomized. It's also double blind, which means you if you were the person doing it, you wouldn't know who is who. And it's controlled is really good too. So, but it's definitely random. Okay? Then, so that's good. Random, check. Are they independent? Those in the placebo, do they affect those that are in the treatment group? And again, no, they won't. Because it's double blind. Remember, double blind means that you, as the researcher, don't know who's who, and the patients don't know who's who. Okay? So, yeah, they're definitely not going to affect the other people because they don't know what they're getting either. Okay? They don't know if they're in the treatment group or not. So it's definitely independent. And then is each sample independent of the other one? So those that are taking the drug, do each one of theirs, I guess you can call it survival, affect the other one? And again, no, because none of them know who's who. Okay? So their survival does not affect another person's survival. So we definitely know that we are independent within each sample. So we are good on CLT, which means that we have a normal distribution. Okay, so there's step 2. Step 3, now it's time to actually find the z-score and figure out the p-value. Okay, so let's talk about how we can do this. Let's do the calculator first. So again, we're going to do number 6. And so here, this is your P1 information. This is your P2 information. X represents the successes, N is the total. So P1, there was 101 out of 110. P2, there was 88 out of 110. Let me just make sure on that 110 that the both of them were that. I'm pretty sure. Yeah, 110 and 110. Okay, good. All right, so we're definitely in step. I need to label this. Yeah, we're definitely in step 3 now. Let me put some order back in this. Okay. And then we were choosing that P1 was greater than P2. And so you can either come down and calculate or draw. So remember I did the drawing one last time. So you can definitely see here is that one tail. Here are the pieces of information we know. Okay. Or again, you can go back and you can just grab the information. Let me show you what that looks like. Okay. You don't have to have it draw for you. And in this one, if you just go and get the information, there's nothing wrong with that because they don't actually show you the pictures in this either. So a little bit more information you get when you actually go and just collect the data. So again, it gives you the z-score, the p. It tells you the p hat. Hey, look, there was that information. We actually didn't have to find it if we didn't want to. It tells you p1 hat, p2 hat, and it gives you the totals that were all used. So this is all that information that would have ran in the formulas right here. Okay. So pretty nice to know that. Oops, didn't want to move on to that one yet. Pretty nice to know that that's there. So let's collect our information, and they want you rounding. It looks like 2 decimals for z-score, which is no surprise. And the p-value could be either 3 decimals or 4 decimals, depending on what they want. Let's do 4. So 0.0059, and then 2.52. So 0.0059 and 2.52. Oops. Okay. So then the last thing, we are in step 4, which is the interpret. So just so you know, p-values are found the same way. Once you have the z-score, you find p-values the same way. That doesn't change here. So step 4, we're going to interpret. Okay. So our p-value is 0.0059. And the question is that less than or equal to, or is it greater than 0.05, which is our significance level? And hopefully you said that it was less than or equal to, which means since the p-value is less than or equal to, we are going to reject the null hypothesis. Okay? We are going to reject it because, and again, you'll have like a fill in the blank here or multiple choice for this piece, because as usual, our my stat lab tells us all the information we need. Those taking IDEL sorry, give me 1 second. did have a significantly higher rate of survival than those taking the placebo. Okay. So we reject, and we know that those that did have a significantly higher rate of survival than those taking the placebo. All right, now there's one more question up here that they ask. It says, can we conclude that IDEL causes an increase? Can we conclude that it causes an increase? Why? Okay. So, in this one, there's a multiple choice piece here. And I'll just read you the choices. There are 5. It says no, because the sample size was not large enough. We know that's not true. B, yes, because a greater portion of ideal patients survived in the experiment. Well, that is true, but let's hang on to that one. Yes, because the study is double blind and uses random assignment. Okay. No, because correlation does not imply causation. You can throw that one out. Okay. Because we're not doing correlations here. This is not a linear model that we're following here. So you can throw that out because this has nothing to do with correlation. Okay. Or no, the null hypothesis was not rejected. Well, we did reject the null hypothesis. So our answer is going to be a yes. We can conclude this. But the question is it because we saw a greater proportion of ideal survive? Or is it because the study is double blind and uses random assignment? And the answer is because the survey or this study was double blind and random as to why we can say it does cause a higher survival rate. So, yes, we can conclude that ideal causes a higher survival rate because the study is double blind and uses randomized assignment, or random assignment, I should say. Because of those two things, that's why we conclude this. Okay, it was very, very controlled. Okay, and that's what we like in our, again, when we run those samples and things like that, we want to make sure that it is controlled and done in the most, how should I want to say, professional way. Okay, we don't want it to yield bias in our results, and that helps destroy that bias. Doing double blind random assignment. And there should actually be a hyphen between those two. Okay, so one of your problems in your assignment is going to be like this. Okay, that's the full gambit of a 2 proportion z-test statistic. That's it. It's a lot like what you did before, just a little bit more work, but not much. Okay, so go ahead and pause the video and give this one a shot. Everything you need is right here on the screen. Okay, so try it and go. All right. So let's start talking about some things. So some of your assignment, just so you know on the questions, they'll actually have you figure out p hat for your first population and p hat for your second population, okay, as well as the null hypothesis estimated value. So they'll have you figure P1 hat, P2 hat, and P hat, the null hypothesis value. So just know that that's some of what they're asking right here. Find and compare the percentages of women who were smiling to men who were smiling, okay? So in this example, it says in 1997 study, people were observed for about 10 seconds in public areas, public places, such as malls, restaurants, to determine whether they smiled during the randomly chosen 10-second interval. The table shows the results for comparing males and females. So down here, it wants us to talk about the proportion of men and women who smile. Okay? So in order to do this, the one thing you're missing up here is you're missing the total number of men and the total number of women. Okay? Total men, total females, or male, female. Okay? So let's get those totals real quick. All we have to do is just add those two numbers up. So 3,269 plus 3,806 give us 7,075 and 4,471 plus 4,278 give us 8,749. All right, so let's start answering these questions and going through some things. And part B is where you actually run the trial, okay, the test. So the first thing says right here, this is what I was talking about a moment ago. This is where they want us to figure out P1, P2, and things like that. So actually, let's figure out who do we want to be P1 and P2. So I'm going to let P1 be the female, smiles, and P2, I will let be the male, smiles. Okay? So those of you that did it the other way around, that just means when it comes to the hypothesis test, when we do the alternative hypothesis, if it is a one tail, your sign will flip from either the greater than to the less than version, or the less than to the greater than version, depending on what happens. Okay? So the first things first, though, it says find and compare the sample percentages of women who were smiling to the men. Okay? So they want us to figure out P1 hat and P2 hat. Well, all you have to do is take those that were smiling for P1, which is all about the women. So that's 4,471. Divide that by the total women, 8,749. Okay? And then for the men, we're going to take those smiling for the men, which was 3,209 for 269 divided by the total for the men, which was 7,075. Okay. So you go to your handy dandy calculator, and I'm just looking up kind of the rounding that they wanted you to do on this. So here it is. And because they're asking for percentages, they're going to have you round to 2 decimal places. All right. Which, when it's not a percentage, that would be 4 decimal places once we do the dividing. So we'll take 4,471 divided by 8,749. And 4 decimal places, 0.5110, which will give us the 2 decimal places as the percentage as 51.10%. Then we will look at the males. We'll take our 3,269 divided by 7,075. And that gives us 4 decimal places, 0.4620, which 2 decimal places as a percentage would be 46.20%. And if they want us to compare this, we would say that the percentage of smiling was greater for the females. Okay? Easy peasy to conclude that. The percentage of space smiling was greater for the females. Okay. So that right there is what part A is all about. All right. And again, you found P hat and all that information. P1 hat, I should say, and P2 hat. Okay. Now we're going to treat this as though it were a random sample and test whether the differences in the proportion of men and women who smile use a significance level of 0.05. Okay. So when they talk about the differences in this, what they are asking you to think about is that they are different. Okay, notice how they didn't say it was one greater than the other. I mean, we observed that the females appear to smile more, but we want to know, is it different? Because technically these are almost half if you think about them. Okay, so when we go to our hypothesis test here, we're going to say, so this is the beginning of part B. This is step 1. That our H naught, of course, as usual, is that the women smile the same as the men. Our ha, yes, we observed that the women smiled more, but what we want to know up here just says test whether there are differences. So that just means, are they different? In other words, not the same. Okay? Because we notice that they technically are not the same up here. So that's what they're looking for here. Not whether one smiles more than the other. That's not what they're asking. They just want to know, are there differences? Okay? All right. So either way, both of these have to be this way. So you guys shouldn't have to worry about a greater than or less than sign, like I was saying, if we switch these around. So if I had this as the males and this is the females, it would be the same down here. Males, females still does not equal. Okay, so there's step 1. So step 2, again, you can check the CLT. So the first thing they want to check is we can check that CLT. Hopefully you did. Successes versus failures. Oh, you know what I forgot to do a second ago? I forgot to tell you the stat crunch. I'll go back and do that stat crunch here in just a second. Okay, actually, I'll show stat crunch on this one. There we go. We'll do that. All right, so successes. So we're going to take, and we need to figure out the null hypothesis value. So we'll take the men or the women who smile, which is 4,471. We'll add that with the men, which was 3,269. And then we're going to divide that by the total number of women, which was 8,749. Plus the total for the men, which was 7,075. Yep. So if we go to our calculator, and I push alpha y equals and put 4,471 plus 3,269 all over 8,749 plus 7,075 and divide that, you get 0.489, and we're going to round to 4 decimal places because that's what they generally like. So there's your p hat value. And so if we check these, pretty easy to check. Take our total for P1, which is 4,471, times 0.4891. Is that greater than or equal to 10? And we'll take 4,471 times 1 minus 0.4891. Is that greater than or equal to 10? So 4,471 times 0.4891. So that's definitely bigger than 10. 2,186.7661. And then 4,471 times 1 minus 0.4891. 2,284.2339. So that's definitely greater than 10. So far, so good. So we've checked population P1. Okay. So now we do the men. And I multiplied by the wrong number. It should have been the totals. But we know that that is still going to be A-okay for this. This should be 8,749. Silly Mr. Armstrong. And this guy's going to be 8,749. So these totals are definitely going to change. But it's still going to be greater than 10. Guaranteed. This guy's going to be around 4,000. This guy's going to be around 4,000, just so you know. But let me actually give you the real numbers because I'm mathematical and that type of nature. I wanted to make sure that it's right. So, like I said, 4,279.1359. And the other one is 749. Can't believe I used the wrong numbers. Such cotton-headed ninny muggins sometimes. 641. There we go. So now let's check the other one. Make sure that I use the right number. 7,075 times 0.4891 greater than 10. And 7,075 1 minus 0.4891 greater than or equal to 10. So if we take those and figure those out, which hopefully you already know that these are going to be greater than 10. So that's 3,460. That's ugly. Let's fix that. 0.3825. Definitely greater than 10. And 3,460. Sorry, I don't know why I'm rewriting that. To get this number, I got to go multiply. So 70, 75. 3,614.6175. So again, it all checks out. So step 1 is awesome. And then step 2, 3, and 4, they're all great as well. Because we already know that the samples are random. Okay, because it says that this was collected randomly. Okay, a random 10-second interval. Okay, and also says treat as though it were a random sample. Okay, so we know that the random is covered. We know that these are independent of each other because whether a male smiles or a female smiles, one does not affect the other. And we also know that it is independent of each other within each sample. Whether a female smiles to another female or anything, their smiles do not affect one another. Okay? We're going to assume that they're independent. Although, I mean, usually if someone smiles at me, I generally smile back. I mean, so they kind of affect each other, but we're going to say we're okay for that. All right? Because we want to run the test. So CLT is all met. Okay? So we're all good on that. So now we're going to jump out to step 3, which is the computing. So we want to find the z-score and the p-value. Okay, so let's do StatCrunch, show you where that's at. So in StatCrunch, you're going to go to Stat, Proportion Stats, to Sample with Summary. So the number of successes for women was, I've already forgotten. For women was 4,471. 4,471. All over the total number of observations. Wrong file. Uh-oh. Okay, we're okay. Which was 8,749. Oh, I see what happened. It pulled it out. 8,000. And I've already forgotten the number because I just got confused. 8,749. There we go. 8,749. And the men was 3,269. 3,269 out of 75. Now here, this is where you got that piece where we're going to say that it's P1 minus P2. So this is where that if you draw that original hypothesis up here, so if all you would have to do is basically just subtract P2 to the other side and you got what's going on. So just so you know, though, when you're doing this, the null hypothesis should always equal 0. So this should not change. All you're going to do down here is put in the symbol that you chose, just so you know. Okay, this should always be 0, and this should always be the symbol, whether it's the greater than, the less than. And even though the P is on the other side, you know, even though the P2 is over here, the sign will not flip. Okay, so if I had less than here, back in there I would choose less than. If I had greater than here, back in there I would choose greater than. Okay. Again, it's all about who is representing your P1 versus your P2. That's the important part. You need to know who is who. Okay? So this is 0, and we want the not equals. And down here, we can ask for some information. We can have it do the, p-value, okay, or it does a bar plot. But we can do the p-value plot for it if we wanted. Okay? We can say compute. And again, you can scroll over. Oh, look, there it is. And you can see where the two tails are at because it's going all the way out here. Okay. So up here, you can also see some other things. Okay. There's our counting and our total, our counting and our total. This right here should be our p hat that we found earlier. So did we find the p hat? Yeah, we did. It's right here. And there it is. Although it seems like my number is off from what they have over here. Let me double check that. Oops, wrong one. Interesting. It is just a little bit off, and that's all right. You can see the Z stat. So don't think of that as your p hat. Okay. This is your sample difference. And there's your standard error. I have a feeling. I got to think about where that's coming from. So to be continued on that part. Oh, here we go. Difference in proportions. So that's taking this proportion minus, okay, that's what that is right there. So this is taking your P1 hat minus your P2 hat. That's that. Okay. All right. So there's that. Yeah. And there's your standard error. And here is the z-stat and the. Now let me talk to you about this. So whenever your p-value is really, really small, like if it's smaller than 0.001, this is what they give you. So they don't actually give you the real value for it. It just says that this thing is super small. Okay. So if we write out the z statistic for this, again, let's write it out to 2 decimals, and then we'll do 4 decimals for this. I mean, but really it's really small. So this where the calculator, this guy might have a little bit of an advantage over that. Let's go ahead and put that information in here and see what it kicks out for us. Because whenever the p-value is really, really small and StatCrunch, they just give it this, which means that it's pretty much like next to 0. Okay. So let's go in here. Let's run this one, and let's see if it actually kicks out the real p-value for it. So our population for women was 4,479, or is it? No, I think it was 749. Let's double check that. 4,400 and wow, I'm getting my numbers all mixed up. 4,471. 4,471 all over. I think this was 8749. I think that's where I was getting that from. 8749. All right. And then 3,269. 3,269 over 7075. And this time we're going to say the not equals, and we're going to go into the calculate. Hey, there we go. There's our p hat. Okay, there's your P1, P2. Yeah, notice it's super small. So here it actually gives us the real value. So I think the calculator probably has a little bit over StatCrunch on this one, because it actually gives us our p hat 1 and our p hat 2, which we figured out earlier. And there's our p hat for the null. But yeah, you can see that this is scientific notation, which means that this is 0.0, or actually 0.9 zeros and then 891. Or so you can see that it's really, 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 really tiny. So if I wrote that out, like I said, your p-value technically would be 0.12345678989. 178 blah 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 blah. 1785. So you can see why StatCrunch said that this is basically less than 0.00, I think 01. Let's go back to that and double check that. Yeah, 3 zeros. And then our Z-stat is 6.13. So 6.13. Okay. So yeah, there we go on that piece. Just so you know, if you do get that really, really small one, you know, like what we have right here for a p-value, what they want you to put in, you would just put 0.000. So 0.000. Those would be your 3 decimal places. Okay. So in StatCrunch or in my math lab, you would put 0.000. Okay. All right. Just wanted to clear that up so you know what to put there. So last step, number 4. Based on what we know, we have 0.000. Our significance level they told us up here was 0.05. So that's definitely less than or equal to 0.05. And that is not a 6, that's a 0. So this means we want to reject the null. Okay? So, in other words, this means that in words, there is significant difference. Actually, say there is a significant difference in the rate of smiling for men and women, males and females. And this should have been in black. Fix that up real quick, because again, I like to be consistent with my colors. There we go. All right, reject the null hypothesis. And there's a significant difference. Okay? So that's the second part. That's what part B is about. Okay? And then they ask us a follow-up question, which if you didn't get to this one, that's okay. Let's answer it now. Explain why there is such a small p-value, even though there is such a small difference in the sample percentages. And this is what we talked about a couple minutes ago, right here. And it's because our sample sizes are huge. The larger that sample size, okay, the larger that sample size, the bigger the denominator you have. And since there was very little difference when we subtracted these two, because this is P1 hat and P2 hat, so because there is very little difference here, our denominator was even smaller. And that drove, when you do the division of a number divided by a really, 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 really tiny number, because our sample size was huge, that drove your z-score way up. So you can see that our z-score was huge. So in that part C, which I'll do, let's do that in red. So in that part C, what you're looking for is something about the sample size. And so again, it's multiple choice. So this is what you'd be looking for. The p-value is small compared to the small relative difference in the proportion, in the sample percentages because of the large sample sizes. And because of that large sample size, it made your denominator really, really small. And that's what part C is about. Just reiterating what we talked about right at the beginning of this. So in here, there is C. And that's what your problems are going to be like, guys. Okay? Just running two tails, providing those pieces of information. Sometimes it's information dealing with CLT. Sometimes it is finding P1 hat, P2 hat, or just P hat in general, as what you saw right down here. You're definitely going to have to find those z-scores and p-values. And again, you got your calculator that can help you out. The calculator gives you pretty much the exact values, where if you're using StatCrunch, you know, if it's really, really low, this is what it does for a p-value. Okay, I think your calculator is probably a little bit. The TI-84 is honestly a better bang for your buck in this. You get a lot of information just from it. So I like the TI-84 for the 2 proportion z-test statistic. So with that being said, the rest of chapter 8 is yours, from question 48 to question 54. Those are all 8.4 sections. So you have all of chapter 8 that's now due. You can now complete the chapter 7, chapter 8 quiz. And we are almost done with statistics. Thanks for stopping by, guys.